Hello, we are from AS1205H, and in this video we are going to present about the high performance liquid chromatography HPLC.
Okay, now we move to the introductions. So, what do you know about HPLC? HPLC, or we call high performance liquid chromatography, is a broad analytical chemistry technique used to separate compounds in a chemical mixture. The HPLC operates based on the principle of chromatography, where a sample is carried by a liquid mobile phase through a stationary phase. This is typically packed in a column. The differential interactions between the components of the sample and the stationary and mobile phase lead to their separation. HPLC is characterized by its high resolution, precision, and ability to handle diverse sample types. It plays crucial in various fields, including pharmaceutical, food safety, environmental analysis, and biotechnology. Due to its capability to analyze compounds ranging from small organic molecules to large molecules, such as proteins and nucleotides. Modern HPLC systems are equipped with advanced detectors such as UV-Vis, fluorescence, and mass spectrometry, which enhance the detection and quantification of analytes. HPLC is expanded by its different modes, including reverse phase, normal phase, ion exchange, and size exclusion.
We move to the objective. In this experiment, it contains three objectives, which is first, to determine the retention time of a standard solution, which is caffeine. Second, to determine the amount of caffeine in soft drink sample using response factor method. And lastly, to identify the caffeine peak in a soft drink sample.
Now I will explain about the component of the high performance liquid chromatography HPLC and their functions. The first part is the pump, which is create the high pressure need to push the mobile phase through the tightly packed column. The next part is the injector that introduce a precise amount of the sample into the mobile phase for analysis. Now is the column, which is the part of the HPLC system where the separation of the sample component occurs. The next part is the detector that identifies and quantifies the separated compounds by measuring a property like absorbance or refractive index. The last part is the data system, computer, that records and displays chromatograms showing detection time and peak areas for analysis. Now let's move on to the experimental, which is prepare a caffeine standard solution. First, a stock solution A with a concentration of 1.0 mg/ml was prepared by 10 mg of caffeine, was accurately weighed and transferred into the 10 ml volumetric flask. Then distilled water was added to dissolve the caffeine, and then the solution was made up to the mark with distilled water. Then we go to the preparing the working solution B, where a working solution with a concentration of the 0.1 mg/ml was prepared. 1 ml of the stock solution A was pipetted into a new 10 ml volumetric flask. The flask was filled to the mark with distilled water. Then for the sample preparation, 10 ml of the soft drinks such as Coke, Pepsi or 100 Plus was poured into a small beaker. A magnetic stirrer was used to remove carbonation, and if need, sonication was applied. Then 2 to 5 ml of the sample was filtered using a 0.45 micrometer pore diameter membrane filter to remove any particulate matter. Now it is time for establishing retention time for caffeine, where the 10 microliter of the working solution B was injected into the HPLC instrument to determine the retention time of caffeine. Then the peak area corresponding to caffeine in the standard solution was measured and recorded. Then, time for soft drink sample to be analyzed, where the 10 microliter of the prepared soft drink sample was injected into the HPLC. The peak area of the caffeine in the sample was measured by referring to the retention time determined earlier.
Hi, so I'll be explaining about the result in discussion. So first thing first, in this experiment, we must look at the caffeine standard. The caffeine standard only shows one peak, which values at 2.482. Next, we must look at the caffeine in cola. There's many multiple peaks in this chromatogram. So we choose the closest one, which is 2.481. Next is the caffeine in Levita. Also the same, has many peaks in the chromatogram, but we choose 2.479. So here is the overall data. We take note about the retention time and the peak area of caffeine. So what to do with all this data? So we need to calculate the response factor RF in caffeine standard. So we do this by dividing peak area of caffeine standard with the concentration of caffeine standard. By referring to the overall data, we just substitute the value, which is 6249.48779 by 1 milligram per mil. So we got is 6249.48779 milligram per mil. We must calculate the concentration of caffeine. We do this by dividing peak area of caffeine sample with the RF value. So by referring to the data, we substitute 7001.1235 with the RF value. So we got is 1.1203 milligram per mil. But we need to change this to ppm. So the final value we got is 1.1203 times 10 with the power of 3 ppm. Next, we must do the same to Levita. So we need to calculate the concentration of caffeine in Levita. So we do this by peak area of caffeine sample, divide by RF value. So we substitute 1.11511 but times 10 with the power of 4 with the RF value. So we got is 1.7843 milligram per mil. So if we change it to ppm, we got 1.7843 times 10 with the power of 3. So what with all these numbers, what does it mean? So 2.482 from the caffeine standards indicates that it takes 2.482 minutes to travel from the injection port to the detector through the column. So the caffeine peaks in Levita 2.479 minutes and Coke 2.481 minutes are identified by matching their retention times to the caffeine standard solution, the closest or the margin value of the peak. For Levita, with a peak area of 1.11511 times 10 with the power of 4, the caffeine amount is 1.7843 times 10 with the power of 3 ppm. For Coke, with peak area of 7001.12305, the caffeine amount is 1.1203 times 10 with the power of 3 ppm. This clearly shows that Levita has a higher caffeine content than Coke.
In conclusion, the present study used high-performance aqueous chromatography (HPLC) to achieve its objective. The retention time for the standard caffeine solution was 2.482 minutes, similar to Coke 2.481 minutes and Levita 2.479 minutes. This consistency shows that HPLC is reliable for detecting caffeine. Coke had a caffeine concentration of 1.1203 times 10 power of 3 ppm, while Levita had a higher concentration of 1.7843 times 10 power of 3 ppm. These results prove that the response factor method works well for measuring caffeine in drinks. The experiment showed that HPLC is an accurate and reliable tool for identifying and measuring components in mixtures. This method is valuable for ensuring the quality and safety of consumer products. I think that's all from us. Thank you for listening.